So welcome to Math12, I think. Mathematics of Lego bricks. So we're talking about how many ways can you build with Legos. So let's start off. We'll assume right now color matters. I have two slightly different grays. How many ways can I combine these pieces? Two. I can put one on top, and I can put one on the bottom. So the first thing we have to talk about when we ask a question like this is, what do you consider the same? What do you consider different? I have deliberately chosen these cylindrical pieces and not the standard square base. If I had a square base, you could then also introduce the rotation. And so, for instance, on the slightly larger 2x2 ones over here, I could actually have infinitely many ways to combine it. And so we were talking a lot about the different rules. If I do it like this, I now have a more complicated problem as to how many ways are there to build with Lego. So we might actually put a rule that things have to be at right angles. When you play Tic-Tac-Toe, how many opening moves are there in Tic-Tac-Toe? I'm sorry? 9. How many moves are there up to symmetry? 3. So I am, I believe, the reigning Tic-Tac-Toe champion at the elementary school playground. I have never been beat. There are 3 opening moves. The 4 corners are all equivalent. The 4 middles are all equivalent, and the center. So you actually have 3 possible opening moves. How many responses? Well, if I go over here, X always goes first. How many responses are there for O? There's now one axis of symmetry along the main diagonal. 5. 1, 2, 3, 4, and 5. Without loss of generality, if I go in the middle, how many responses are there? 5 again. 1, 2, 3, 4, and 5. And for completeness, we'll do the easy case where you now go in the middle. 2. So there's 12 pairs of opening moves. Much better than 9 times 8 is 72. So when we do the game in Lego class for the first and second graders, this is a great thing to talk about, is how do you analyze? Now we said symmetry doesn't matter. That if I go over here in the middle, then either these 2 corners is the same, but that's different than here. This is what I'm not touching. There is a difference. Do you think for a game like Tic-Tac-Toe that symmetry is fine? That really there's no difference between playing this versus playing this? How many people play cards? Anybody here play bridge? Or whist? Hearts? Spades? Okay. Is there anybody here who does not know what a deck of cards looks like? What are the suits in a deck of cards? Yes. If I were to change to carrots, cucumbers, broccoli, and cauliflower, would it change the play of any of the games? No. But for non-experts, it often throws them a little bit, because they're used to seeing certain things. So how you present things can matter. But in terms of the analysis of the game, does it matter if we call things spades, hearts, diamonds, clubs? No. One of my favorite examples, and I'm pretty sure you've seen this from 150. How many of you have done Sudoku? Okay, everyone has done a Sudoku. We use the numbers 1 through 9, correct? If I'm doing a Sudoku, lots of stuff. If I want to make sure that a row is correct, how many checks do I have to do for a row? You give me a proposed, I think I've solved the Sudoku. How do I tell if you're correct? How many checks does it take to make sure that row is correct?
3.
Okay, why 3?
Column, row, and box.
Right, but for each row, how many things do you have to check for each row?
8.
I'm sorry?
8.
Why 8?
Because there are 8 neighbors.
But so how do you know if a row is valid?
If they're all unique.
If they're all unique. So how do you tell if they're all unique? So in theoretical mathematics, we could just say, make sure they're all distinct. Fine. Several of you have raised your hands. Raise your hands if you're thinking of computer science as a possible major. You need to be able to program things. You need to be able to give explicit instructions to the machine. How does the machine tell if they are distinct?
As you go, you kind of create a list of every number you've seen so far and check. Oh, that's more than 8 checks, I guess.
So you could check, do I have a 1? Do I have a 2? Do I have a 3? Do I have a 4? And if you have one of each, you only have 9 spots. You don't have infinitely many. If you have at least 1 1, at least 1 2, at least 1 3, at least 1 9, you're done. And in fact, as soon as you see 2 of 1, you can stop. You can actually check a row with 1 step rather than with 9 checks. And the point is not to use the standard numbers 1 through 9. Use 1, 10, 100, 1,000. If your numbers sum to 111,000,000, 111,000, 111, the only way that can happen is you have one of each. From an implementation perspective, this is much easier to check. From a practical perspective, it makes no difference. So this is something I want you to be thinking about whenever you're doing work. What really matters, what's a convenience? Now, anybody here a potential chemistry or biology person? Okay. There are these things called compounds and molecules. It's almost at the level of my knowledge. But for some of them, if you take the mirror image of the compound, it's not going to fit into the way your body is designed, because this is not an abstract molecule floating in space. This is a molecule meant to actually try to do something. And so the mirror image could actually kill you rather than save you, because we're not looking at something in isolation. So when you're counting, you might, for something like this now, want to consider mirror images as distinct. Or maybe it depends on what kind of symmetry there is. So is there a difference between the following? Versus these pairs. Do we agree that the 2 top are equivalent? Do we agree that the 2 bottom are equivalent? Are they equivalent in the same way? How do you make the 2 top equivalent? What do you do?
Horizontally.
So what does this mean? Are you like Queen Victoria?
You're reflecting across that vertical axis.
And by reflecting across the vertical axis, you're actually moving a 2-dimensional object through a 3-dimensional space. Is there anybody who has a difficulty taking a piece of paper and moving it into? Okay, I'm pretty sure the prerequisites for the class cover stuff like that. They do not cover taking a 3-dimensional object and flipping it in a 4-dimensional space, right? So we can talk about this, and we can. Anybody ever see the movie Flatland? You've seen it? Who plays Hex? Who's the voice of Hex? It's Kristen Bell before she became Anna from Frozen. So if anybody's interested, I have both Flatland and the sequel to Flatland. It's based on a story from maybe 150 years ago about creatures that live in a 2-dimensional world. And in the sequel, you go into even higher dimensions. So it's a very interesting challenge for animators as to how you do something like that. But in the other ones, they talk about reflecting things in a 3-dimensional object through 4-dimensional space. Here, this is not a bad reflection for us to do, but if you are confined to live on the plane, you cannot do that reflection. You can still do the analysis as being equivalent, but you can't actually do that reflection formally. What about getting from here to here? This is also flipping it through 3 dimensions. So is this equally bad?
But you can just rotate it.
Yeah, but just because we can flip it through 3 dimensions doesn't mean that's the only way we can get there. We can also get there by just turning it 180 degrees. And so we can actually go from here to here within the plane. So in terms of trying to count how many ways there are to do things, so one of the big questions in Legos is how many ways are there to stack things? So if we assume all the bricks are the same color, and let's assume things have to be at a right angle, we can start constructing a sequence. If I give you everything that's a 1 dot, how many ways are there to do it if you have n objects? 1, right? The only choice you have is to just keep adding them on top of each other. It's really not challenging. So part of this class is to give you a little sense of how mathematicians think. So if we have only 1 by 1 bricks, the sequence of the number of ways we can do things is quite boring. Let's look at 2 by 1 bricks. So if we only have 1 2 by 1 brick, it's 1. Now let's say we have 2 of them. How many ways can we combine 2 bricks?
2?
6.
Are we assuming that the 2 bricks are
We'll assume they're the same color
interchangeable?
and interchangeable.
7.
All right, so we clearly can put one on top of the other perfectly. All right, so we've clearly got as one possibility. What else could we do?
You can still either and rotate n.
So without loss of generality, you might as well assume the bottom one is oriented like this. And then the top one, we can either place on the first or on the second. We can go, so if we place it on the first over here, it can go out like this, it can go like this, and it can go like this. This going out is clearly different than this. Do we consider this the same as this? It comes down to how you want to count things. And you get a different answer depending on your choice. So a lot of times you can have 2 people disagree as to what the answer is because they have different metrics of counting. Do you think that for our purposes we should count these as the same or different?
Different? Yeah.
Okay, I would have gone with the same, but we'll count them as different. All right, overruled. So this would give us 3 different possibilities from that. Now if we put this piece over here, if I rotate this 180 degrees, that's clearly going to be the same. So now we would have 1, 2, 3 more ways from this, and that's it. So we would have 4. If we counted this and this is the same, I think we only have 3 now. And so you can get 2 different sequences. There's a wonderful web page called the Online Encyclopedia of Integer Sequences. I think it's oeis.org. And if you put in strings of integers, it will tell you all the strings it knows in its memory. That's have either that as the start or have those numbers consecutive at some points. There's lots of different things you can do. A classic problem in the subject was if I give you 6 2 by 4 bricks, how many ways can you combine them? And this was done, I think, very early by Lego as a way to just kind of sell how many different ways you could play. Well, a lot of them suck, But it wasn't clear. Do they have to be connected? Could I have 4 bricks all connected here and 2 bricks connected over there? What if I force right angles? Do I consider something like this equivalent to something like this, which is from reflection? So there are some really good theoretical papers, and if you're interested, let me know, I'll send them to you, that actually talk about how do you compute the answer to a problem like this. In principle, it's trivial. How would you solve it in principle? I don't care if you can actually do this. In principle, what would you do? Just count them. Just go through and physically look at every possible one, store it in memory, and then find some way to tell if two different shapes are equivalent. Look at reflections and whatnot. And it may be difficult to figure out initially if two things are equivalent. What is the math needed to say, is this shape equivalent to this shape by reflecting about some axis? It is not always an easy question to determine if two things are the same. How many of you remember your equations of conic sections? Your equations for ellipses and hyperbolas? If I'm feeling generous, I'll give you an ellipse aligned with the coordinate axes. And then the equation of the ellipse is x over a squared plus y over b squared is 1. And this is a, b minus b. If you know linear algebra, if I give you the rotated ellipse, it's not so bad. There are other ways to write down the equation of an ellipse. And you can use something called the eccentricity of the ellipse. And when Kepler was looking at the orbit of Mars, he was like, oh crap, if only the orbit of Mars was an ellipse, I would really know what's going on. But unfortunately, it's a different shape. It was actually an ellipse, but he didn't recognize that it was an ellipse because it was not the way he was used to seeing an ellipse written. And given how early the idea of equations and writing things down like this in algebra and Descartes' work, it's not surprising that these things were not second nature. How you present things can matter. And it can often be a real challenge to prove that two things are equivalent. And so by brute force, we can enumerate all possibilities. We don't care if the universe will die a heat death before things end. And we'll look at all the different ways maybe to rotate things and try to line them up and see if they're the same. But it could be a very difficult problem to tell if two things are the same. This is often done in graph theory, trying to determine if two graphs are isomorphic. Is there a way to tell if one is the same as another? Another place where this occurs is wonderful question in quantum mechanics. Can you hear the shape of a drum? So if you know the frequencies that a drum vibrates, and if I give you that sequence, does that uniquely specify the drum that gives it? And there's a whole slew of questions as to when the answer is yes, when the answer is no. So in terms of trying to give some theory, one way we can go if people want to do some theory is we can talk a little bit about how you would do problems like this. Or how would you analyze a game like Tic-Tac-Toe? What can you do to make Tic-Tac-Toe interesting? So is there anybody here who feels that they can beat me at Tic-Tac-Toe? No one wants to try? Okay. Usually I can get an elementary school kid to say, I can take you. I will just mention a few quick ways to make Tic-Tac-Toe interesting. And for those of you who are coming to the first and second graders, we might do some of this stuff with them. So one possibility is in each square of the tic-tac-toe board, you have a tic-tac-toe board. All right. Somebody who hasn't spoken in a while, tell me where you want to go for your opening move. It's okay if it's not a good move.
I'll go in the very middle.
Yeah, I think you would say center.
Yeah.
So because you've gone in the middle of this board, I now have to go somewhere in the middle of this board. So I've got to go in one of these 8. So I'll go here in the upper right corner. Now it's your turn. Because I went in the upper right corner, you now have to move somewhere in here. And whatever square you move on, if it's available, I will then move. I will play poorly.
Okay. I'll go in this. Can I go in the center?
You can, but that's going to make it hard for me to play poorly, so please don't go in the center.
Okay. I'll go bottom right corner.
Bottom right corner. All right. I will go in the center. I'm deliberately playing poorly. Now you have to move in the center.
Oh, okay. I'll go bottom right corner.
All right. Well, now if you go bottom right corner, I get to play again in here.
Top
You're making
left.
it hard for me to lose to you.
Top left.
Top left. All right. So looking at here, I clearly do not want to go in the center, because if I go in the center, I just want to make sure, because this is being recorded, I am deliberately playing poorly. I will go over here, seizing the center. And now your turn.
Bottom right.
So now, there's several different versions. One version is you've now won, you have 3 in a row. The other version is now the center becomes a giant X, and you keep playing. And then you have to decide what are the rules if you need to go into a board that's no longer free. Maybe it's then a free move and you can go to any board you want. And then can you get 3 in a row in something like this? So this is one way to make tic-tac-toe more interesting. Right? Another way to make tic-tac-toe more interesting is to play on a larger board. Play on a 20 by 20 board and you have to get 5 in a row. If you play on a larger board, you could actually help whoever's going later. Just put in a bunch of lines. Maybe you put in a couple of O's far away from the center. And so the game starts off, you're being played, this. And so initially, player 1 has an advantage because they've gone first, but if you have some O's further out, if O can get the game to last long enough, maybe O can move to where O has some strength. So that's one way to try to handicap the game. The last one I'll talk about is bidding tic-tac-toe. So in bidding tic-tac-toe, we each start off with a certain amount of money. Let's say we each have $1,000. At the end of the day, it doesn't matter how much money you have, it just matters did you win or lose. And you bid for each move. Whoever bids most gets the move. And in one version, you give the money to the banker. In the other version, you give the money to your opponent. All right? Anybody want to play me? I will play very poorly. All right. I've decided how much I want to bid.
Oh, so both people decide first how much they're bidding?
Yes, and you keep it secret. Have you decided your amount?
Yes.
Okay, can I trust you? Okay.
I bid $300.
Okay, I really wanted the opening move. I bid $999.
Oh.
So I get the opening move. Ha 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 ha. I now have $1. You have $1,999, and I am going to grab the center.
Okay. I bid $1,900 on let's say the top left. Where do you want to go?
Okay, so wait, you don't have to tell me which move. Do you want to bid $1,900?
I mean, I can bet 2. I can bet.
Right. You can just bet $2.
Oh wait, if I win, I give it to you, don't I?
Yes.
That's right. No, I don't want to do that.
Yes. So I was about to say, hell, I might actually win this one.
Yeah. No. I bid 2.
You bet $2. All right. So now I go up to $3. Where do you want to go?
Oh, let's see. Are cards or size better? I don't know.
Not going to really matter.
Yeah.
You really have to work to blow this. You could probably get every square with the amount of money you have over me.
Yes.
Right? How much do you bet on your next one?
I'm going to bet 4.
Right. So I now go up to 7. You go down to 3. Where do you want to go?
Top left.
Right?
Mm-hmm.
And what you can do is you can even toy with me, and you can keep going in other places.
That's what I was thinking.
Yeah. That's why I'm going to stop here. So, in some versions, they actually have a chip, so that if it's a tie, if you have the chip, you get to decide whether or not you want to win or you want the other person to win. I actually don't like that version. It makes the game solvable, but it has an asymmetry. The two players are not equal. There is a difference of being player 1 and being player 2. I like if we both bid the same amount, then we have to rebid, which means the game might never end. How could I make this fair for me to play against first and second graders? Yeah, if I start off with $1,000 and I give them $2,000, this is a way to actually have like golf, like a handicap in tic-tac-toe. You could, of course, also maybe give the little kid an extra move in tic-tac-toe, but I think if you give a kid an extra move in tic-tac-toe, the game is not going to be that interesting. So there are variants of these games that become interesting, and they all come down to, in some sense, counting. And so these are some of the interesting problems we have with stuff like this. All right. Let's stop.